This is the most significant stress test we have seen yet. As of January 24th, we are looking at the immediate aftermath of a massive solar intersection that has just concluded in the distinct region of space occupied by 3I Atlas. This is not just another space weather update. We have just witnessed a direct, high-energy collision between a major solar event and our interstellar visitor, and the telemetry pouring in right now is painting a chaotic picture. Earlier this week, specifically on January 20th, the Sun unleashed a powerful X 1.95 class solar flare. This was not an isolated burst. It was accompanied by a full halo coronal mass ejection that launched a dense cloud of plasma directly along the Sun-Earth line. The timing here is critical to understand. On January 21st, the shock front of that plasma cloud, riding the wave of an intense radiation storm, slammed into the precise coordinates of 3I Atlas, which is currently positioned roughly halfway between the orbits of Earth and Jupiter. We are talking about an influx of high-energy protons that shattered recent records. The National Oceanic and Atmospheric Administration declared a critical weather day here on Earth because the particle flux levels spiked to nearly 200 times the standard warning thresholds. This is the most intense radiation storm of the 21st century so far, and 3I Atlas was caught squarely in the crosshairs. Let us look closer at the data coming from our space-based observatories. The images we are receiving are currently filled with noise, a phenomenon astronomers refer to as a snowstorm effect. This happens when high-energy particles physically strike the detectors on our telescopes, creating bright streaks and false signals that wash out the faint details of the target. While this makes standard optical observation difficult, it tells us exactly how violent the environment around the comet has been for the last 72 hours. The planetary K-index, which quantifies disturbances in Earth's magnetic field, peaked at levels approaching a severe G4 geomagnetic storm. But why is this bombardment so important for us right now? Because we are treating this radiation storm as an active experiment. We usually have to wait for the object to do something on its own, like outgas or rotate, to learn about its internal structure. This week, the Sun did the work for us. It stripped away the calm. It subjected the surface of 3I Atlas to a bombardment of charged particles that would strip the tenuous atmosphere off a lesser body. We are watching to see how the object responds to this energy injection. Does the coma brighten significantly efficiently? Do the jets destabilize? Or does it shrug this impact off with the same anomalous resilience it has shown since perihelion? If you are following the minute-by-minute updates on this channel, you know we analyze these raw data sets as they come in. If you want to keep up with this rapidly evolving situation, make sure you represent the subscribers who want the deep analysis by hitting that subscribe button right now. We are going to be breaking down the spectral data as soon as the noise clears. The dense central core of that plasma cloud has now continued past our position. It is moving outward and will brush past Jupiter in the next few days. But for 3I Atlas, the peak of the event has passed, and we are now in the crucial observation window where the after effects become visible. The geomagnetic conditions are stabilizing, but the scientific excitement is just hitting its stride. The interaction between a charged solar wind and a cometary ion tail is complex enough, but when you introduce a density spike of this magnitude, you expect to see dramatic disconnection events where the tail is literally ripped away from the nucleus. So, what does this actually mean for the observations we are trying to make today? It means the immediate environment around the nucleus is currently supercharged. Any volatile materials on the surface have just been subjected to intense heating and sputtering. We are not just looking at reflected sunlight anymore. We are looking at a system that has been electrically and thermally shocked. This is our best chance to see what lies beneath the crust. If there is a protective layer, or if the composition is denser than regular cometary ice, the resistance to this storm will betray those properties. We are waiting for the clean feed to verify if that distinctive anti-tail has survived the onslaught intact. Everything we know about cometary physics suggests that a structure as fragile as the one we have been observing should show massive disruption after an event like this. If we look at the fresh images clearing up tomorrow and find that the geometry remains rigid, we are going to have a very serious conversation about structural integrity. The storm was the hammer, and 3I Atlas was the anvil. Now we find out what the anvil is made of. The scientists monitoring the feed are currently calibrating for the interference, but the early indications suggest we are about to see something that defies standard solar wind dynamics yet again. Focus on the timeline. The impact was January 21st. Today is the 24th. The delay in clean data is purely due to that snowstorm effect on the sensors I mentioned. As that interference fades, we will get our first clear look at the post-storm configuration. This is the moment where the models either hold up or break down completely. We are not just watching a rock drift through space, we are stress testing a hypothesis, and the sun just provided the perfect variable to test it against. Stay with us as we move into the structural analysis in the next report. The storm was just the catalyst. The real story is the reaction. As we established, the radiation storm has acted as a massive celestial stress test, and now we need to assess the damage, or rather, the lack thereof. This brings us directly to the anomalies that make 3I Atlas so confounding. The heightened interest in this entire event is not just because a storm hit a comet. It is because that comet was already behaving in ways that do not conform to any standard astrophysical models we have. This new influx of energy serves as a diagnostic tool for the features we have been tracking for weeks. Let us start with the most glaring anomaly. Before this solar storm hit, observations had already confirmed an unusual anti-tail extending roughly 130,000 kilometers. Now, keep in mind, a standard dust tail points away from the sun, driven by radiation pressure. An anti-tail, optically, appears to point toward the sun, usually due to a perspective trick when Earth crosses the orbital plane. But what we are seeing here is persistent. It is pointing toward the sun in a way that challenges our understanding of solar wind dynamics. If this feature were merely a trail of heavy dust particles left behind in the orbit, the coronal mass ejection that just swept through should have scattered it. Theoretically, the pressure from that plasma front should have disrupted the coherence of a distinct structure like that. Here is the crucial detail we are looking for in today's downloads. Did that 130,000 kilometer spike waver? If observed data shows that the anti-tail has maintained its integrity despite the massive increase in solar wind density and velocity, we have to rule out loose, fluffy dust aggregates. Normal cometary dust is micron-sized. It gets pushed around easily. If this structure held firm against the most intense radiation storm of the 21st century, we are looking at something much more massive, or held together by forces we are not currently accounting for. Then there is the matter of the jets. We have observed 3 symmetric jets of material, spaced at angles of approximately 120 degrees. This is a configuration that is atypically precise for natural cometary activity. Nature is rarely so geometrically perfect. Usually, jets erupt from random weak points on a warming nucleus, creating a chaotic, lopsided coma. A symmetrical tripartite distribution implies a uniform internal structure or a very specific rotation state. This contradicts what we previously thought about random outgassing. Now, apply the storm logic to this. The intense heating from the solar flare event should have triggered new, random outbursts. It should have destabilized that symmetry. We should be seeing a chaotic brightening all over the surface. If the fresh imagery reveals that those 3 jets are still firing at 120-degree intervals, unaffected by the chaotic energy unplanned injection from the sun, it suggests that the mechanism driving them is not a simple surface sublimation response. It implies deep-seated stability. This connects to the rotational orientation. We know the object's spin axis is directed almost precisely toward the sun, deviating by only about 20 degrees. This is what we call a pole on orientation. For a natural object tumbling through the void, acquired in interstellar space millions of years ago, the probability of such an alignment pointing right at our star right now by chance is considered extremely low. It is statistically uncomfortable for many dynamicists. Think about a gyroscope. It resists changing its orientation. 3I Atlas has maintained this axis despite the varying torques of its approach. The question on everyone's mind is whether the torque from this recent solar storm, the sheer physical push of the plasma cloud, was enough to induce a wobble. If the spin axis remains locked at that 20-degree deviation, we are dealing with an object with a significant moment of inertia, effectively a heavy, balanced flywheel. So, why does this matter right now? Because we have a control group and a variable. The control is the quiet cruise phase we watched in December. The variable is the storm. If the behavior is identical in both scenarios, the internal mechanism of 3I Atlas is robust beyond the level of a loose rubble pile comet. We are looking for changes. We are hunting for a wobble, a flicker, a disruption. And so far, the preliminary curves are terrifyingly smooth. I want to pause here and ask you a question. If this object ignores the strongest solar storm in 2 decades and maintains its perfect geometry, what is your threshold for proof that this is not natural? Let me know in the comments below what evidence you would need to see to be convinced one way or the other. We are reading them as we piece this together. We are narrowing down the possibilities by elimination. If it is not a dust cloud, and it is not a standard outgassing comet, the list of natural explanations gets very short and very exotic. We are looking at potentially metallic compositions or dense monolithic structures. And that leads us directly to the observational geometry that happened immediately after the storm peak. Because just as the smoke cleared, the Earth moved into position to give us the wildest view yet. We are about to look directly down the barrel of the gun. The alignment on January 22nd gave us a perspective that might finally resolve the surface composition. That is what we are breaking down next. Use this time to verify your subscription status because the next monitoring report is going to be dense. Building on this idea of geometry, we have to talk about the observational miracle that occurred on January 22nd. While the radiation storm was the hammer blow, the orbital mechanics gave us the perfect lens to inspect the cracks. A key observational moment occurred just 48 hours ago when Earth lay almost exactly on the line between the Sun and 3I Atlas. This is what astronomers call opposition, but this was not just a standard pass. The phase angle, the angle between the light source, the object, and the observer, dropped to less than 1 degree. To put that in perspective, seeing an object with a phase angle of 0 is like having the sun directly behind your head while you look at something. It maximizes the illumination and eliminates all shadows on the surface of the target. You see everything. This presented scientists with a rare opportunity to closely examine the structure and composition of the object's emissions. We refer to this as the opposition effect or the opposition surge. When shadows disappear, brightness usually spikes nonlinearly. The way that brightness spikes tells you about the texture of the surface. A rough, porous surface like our moon brightens dramatically. A smooth, icy surface behaves differently. Given what we now understand about the radiation impact on January 21st, the timing of this alignment on January 22nd is almost poetic. We got a full frontal illumination of the comet exactly 1 day after it was scrubbed by high-energy plasma. The timing means we are seeing a fresh surface. Any loose dust that might have obscured the true crust was potentially scoured away or electrically levitated by the storm. And then, immediately, we turned the spotlight on it. So, what does this actually mean for the data we are crunching? It means we are looking for the coherent backscatter peak. That is the scientific term for the way light bounces straight back to us. If 3I Atlas is a loosely bound pile of ice and rock, that light should scatter in a diffuse, predictable way. But the early indications from the high-gain antenna feeds suggest the reflection was sharper, more specular, almost metallic in nature. Let's look closer at the data regarding the coma, the atmosphere around the comet. With the sun strictly behind us, we can map the density of those 3 symmetric jets with 0 perspective distortion. We are looking straight down the rotation axis. If those jets are indeed spaced at 120 degrees, this view would show them as a perfect Mercedes-Benz logo in the sky. Any deviation, any warping from the solar wind would be instantly visible. This is the definitive text on the object's symmetry. We are not inferring angles from a side view anymore. We are looking at the blueprint. And the fact that this alignment happened while the object was still reeling from the particle flux event allows us to see if that plasma cloud stripped away the outer layers of the jets. Did the jets waver? did the structure buckle? This view also allows us to probe the size of the particles in the tail. The way light scatters at small phase angles is very sensitive to particle size. We can differentiate between cigarette smoke-sized particles and jagged gravel. It was anticipated that the detection of anything beyond water ice and fine dust, such as large particles or complex materials, could significantly influence interpretations of the object's origin. We are looking for the spectral signature of something durable. If the brightness surge was higher than expected, it implies a surface that is highly reflective, perhaps distinct from the dark organics we usually find on comets. We are hunting for the glint of metal or processed materials against the dark backdrop of space. The opposition surge is the flash photography that reveals the details hidden in the shadows. It is rare to get an opposition this perfect for an interstellar object. The last time we had a visitor like this, we missed this kind of geometry. This time, we caught it, and we caught it right after a solar storm. The combination of these two factors, the stress test and the perfect lighting, has given us a data set that is currently the most valuable property in the scientific community. The calibration of this brightness data is tricky. We have to subtract the noise from the storm, which we discussed in the first report. But once that noise is gone, the signal that remains is the true face of 3I Atlas. We are effectively reading the license plate of a car moving at interstellar velocities while it drives through a blizzard. And we think we just got the numbers. In the next segment, we are going to talk about exactly what those numbers imply about the stuff this thing is made of. We are moving from how it looks to what it is, because if that reflection is not ice, we have to ask what else shines that brightly in the void. As we move from geometry to chemistry, the mystery deepens. We are now focusing on the physical substance of 3I Atlas. What is it made of? The opposition data from January 22nd is the key to unlocking this, and the initial readouts are forcing us to discard the simple, dirty snowball hypothesis. We are looking for complex materials. The expectation was straightforward. A comet is mostly water ice, carbon dioxide, dust, and maybe some trace organics. It is primordial leftovers. But the spectral analysis we are conducting in the wake of the radiation storm is hunting for signatures that do not belong. We are looking for complex materials. Researchers emphasized that the detection of anything beyond water ice and fine dust would be a game changer. Specifically, we are looking for the thermal inertia signatures of large particles. Fine dust cools down instantly when it rotates into shadow. Solid rock or metal holds heat. It has thermal memory. The data collected during the close alignment allows us to measure this thermal lag with unprecedented precision. If 3I Atlas were a fluffy aggregation of dust, its thermal signature would drop off rapidly. But if the data shows a high thermal inertia, it suggests the surface is solid, dense, and potentially metallic. This connects to the anti-tail we discussed. That 130,000-kilometer spike pointing toward the sun requires heavy particles to sustain itself against the solar wind. We are not talking about smoke. We are talking about gravel, pebbles, or perhaps something artificial and continuous. Let us look closer at the data regarding the spectral absorption lines. Spectrometers on our space telescopes split the light reflected from the comet into rainbows. Dark lines in those rainbows correspond to specific chemical elements. We are used to seeing lines for hydrogen, oxygen, carbon. But in the aftermath of the storm, as the surface was bombarded by protons, we are looking for fluorescence, X-rays emitted by elements glowing under the solar assault. This is where the X 1.95 flare becomes our ally. The solar X-rays hit the comet and excite the atoms on the surface. They scream back their identity. If we detect high concentrations of iron, nickel, or titanium in the coma, it would be unprecedented for a comet. These elements exist in comets, but usually locked deep inside dust grains. To see them in the gas phase, or as a primary component of the reflection, would suggest verify a composition that is far richer in metals than any natural icy body should be. This contradicts what we previously thought about the object's formation. Comets form in the outer edges of planetary systems, where ice dominates. They are not metal foundries. A metallic signature points to a different origin, perhaps the shattered core of a dead planet, or, as some speculate, an artificial alloy. So, what does this actually mean for the three jets? If the material spewing out is not sublimating ice, what is it? Some models suggest we might be seeing ion propulsion or some form of magnetic exhaust if the object is artificial. While we must remain skeptical, the absence of water vapor in quantities matching the visual brightness is a red flag. If it is bright but dry and rich in heavy elements, the comet label starts to peel off. We are currently waiting for the integration times to finish on these spectral charts. The signal is faint, but the spikes are distinct. We are seeing hints of complex hydrocarbons, plastics, or tars, mixed with that metallic regolith. The complexity of the molecules surviving the radiation storm is another puzzle. High-energy protons usually break complex chains apart. If they are reforming, or if they are being replenished from the interior, the chemistry is active. This is not a dead rock. It is a chemically dynamic system that is reacting to the solar environment in real time. The focus of the current analysis is to determine the ratio of dust to gas. A normal comet is mostly gas with some dust. 3I Atlas appears to be dust-rich, but that dust is behaving like heavy grit. As of January 24th, the research teams are still calibrating. They are subtracting the background signal of the plasma cloud itself. But the raw feeds indicate a composition that is far too ordered and far too heavy for the standard models to explain comfortably. We are on the edge of identifying the skin of the visitor, and if that skin turns out to be a titanium alloy shell instead of a crust of dirty ice, history changes today. If you are enjoying this deep dive into the science of the unknown, please take a second to like this video. It helps other explorers find this content. We have one final chapter to cover: the implications of it all. Where does this leave us? Is it aliens? Or is nature just smarter than we are? We will wrap this up in the final segment. So, here is where we stand. We have an object that has weathered a massive solar storm without flinching. It has a tail pointing the wrong way, jets that remain geometrically perfect, a spin axis locked onto the sun, and a composition that hints at heavy, complex materials. As of January 24th, researchers emphasize that all collected data are still undergoing calibration and analysis, but the silence from the official channels is deafening, and the raw data speaks volumes. We have to address the elephant in the room. Does the observed behavior of 3I Atlas point toward more exotic origin scenarios? The answer lies in the combination of anomalies. Any single one of these things, the anti-tail, the alignment, the resilience, could potentially be explained by a freak natural occurrence. You could have a weirdly shaped asteroid. You could have a lucky collision that spun it up. You could have a dust trail that looks like a jet. But when you stack them, when you have 5 or 6 sigma anomalies piling up on top of each other, the probability of natural factors drops to near zero. Occam's razor suggests the simplest explanation is usually right. But is it simpler to invent 5 new distinct natural astrophysical mechanisms to explain one rock, or to admit that the rock might be a machine? More detailed spectral and dynamical results are expected to be published in the coming days. These papers will likely be conservative. They will use phrases like anomalous dust properties or unexplained angular momentum. But read between the lines. They are describing a structure that is engineered. The spin axis deviation of 20 degrees is the smoking gun for many. A solar sail, designed to harness light pressure for propulsion, would need to face the sun. But it would also need to tack, to angle itself to steer. A 20-degree offset is a steering angle. It provides a lateral thrust vector. If we see that angle change in response to the orbital position in the coming weeks, we are watching a vessel navigate. The radiation storm was the variable we needed. A natural object is passive. It gets pushed around. An artificial object has mass, inertia, and potentially active stabilization. The stability we witnessed this week suggests the latter. 3I Atlas did not tumble. It did not break apart. It took the hit and kept its course. Reference the jets again. If they are thrusters or exhaust vents, their symmetry makes perfect sense. 120 degrees is the ideal configuration for 3-axis stabilization. Nature does not care about stabilization. Engineers do. We are entering a period of maximum scrutiny. The data from the critical weather day and the opposition alignment is going to be scrutinized for decades. But right now, in this moment, we are living through the discovery. The pieces are on the table, and the picture they form is becoming undeniable. This is not just science news. This is potentially the most important discovery in human history, unfolding in slow motion. We will continue to monitor the spectral releases moment by moment. If a specific heavy isotope is confirmed, or if that rotation axis shifts by a single degree to correct for the storm, we will be back with an emergency update. Until then, keep looking up. The universe is getting crowded, and it seems our neighbors might be passing through. Thank you for watching this deep dive. If you want to support this channel and ensure we can keep processing this raw data, please like this video and share it with someone who needs to know what is really going on out there. Stay curious.